I'm Pamela Hughes, Director of Friends Programs, and it's my pleasure to welcome you and introduce our speaker, Douglas Stanford. After receiving an undergraduate degree at Stanford University, Dr. Stanford was honored with a Marshall Scholarship and studied at the University of Cambridge, where he earned a master's degree in physics. He then returned to California and continued his studies at Stanford University, where he earned a PhD in 2014. Since that time, Dr. Stanford has been a long-term member at the Institute, with funding this year provided by the Simons Foundation. He'll return to Stanford University at the end of this year, where he's been appointed Assistant Professor of Physics. His research is focused on quantum gravity, quantum field theory, and string theory, and he has worked on the ADS-CFT description of black hole interiors and the relationship to chaotic dynamics in quantum field theory. While at IAS, Dr. Stanford has collaborated with other members and faculty and written numerous papers. His recent and excellent article, which I commend to you in the spring issue of the Institute Letter, prompted this invitation to speak. And I've put out extra copies of that newsletter if you didn't see it, and you can please take another. On behalf of the Friends, I'd like to thank Dr. Stanford for taking this time to speak to us today, to kick off the Friends program of events for 2017-18. And I'd also like to extend special thanks to the Simons Foundation, whose generosity has helped to make David's year at the Institute possible. Please join me in welcoming Dr. Douglas Stanford, who will speak on black holes and the butterfly effect. There will be a period for questions and discussion afterward.
Thanks very much for the introduction. I'm really excited to get a chance to share with you guys a little bit of what some of us have been working on in the School of Natural Sciences. I know there's a period for questions at the end, but I really hope that you will ask questions if they arise during the talk. It will sort of help me get back on track if I'm getting off course. Mainly we're going to be talking about chaos and the butterfly effect in the context of black holes and strongly interacting quantum systems. But I want to start by discussing it in the context of science fiction. So there was a short story written by Ray Bradbury in 1952. It's called The Sound of Thunder. And the plot goes like this. It's the year 2055, and people have figured out how to build time machines so they can do time travel. And the main character of the story, who's called Eccles, signs up to go on a hunting trip 60 million years ago because he wants to shoot a dinosaur. He wants to shoot a T-Rex. So he signs up with this company. They go back in time, and he goes with a guide. The guide is super paranoid that they're going to affect something in the past because that could have some consequences in the future. So, for example, they pick a T-Rex to shoot that is going to get hit by a tree and die like a couple of seconds later. So they're very careful about this. But our main character, Eccles, makes a small mistake. And when they get back in their time machine and travel back to the year 2055, he discovers that he's stepped on a butterfly and crushed it, and it's stuck to his boot. And the guide is horrified, and when they emerge from the time machine, they discover that the world has really changed. So in the story, it changes in like very subtle ways, like the spelling of words are different, the person who's won a recent election is different, and the guide is so upset that he shoots Eccles, and the story ends. So I think this is a wonderful story because it gets a lot right about chaos and the butterfly effect. So the basic idea that small changes to the state of a system can have large changes, can have large consequences in the future. So in this case, the small change was crushing this butterfly with the boot. But there's this great quote in there in the story, which is something like, any small error will be multiplied over 60 million years, completely out of proportion. So the notable thing about this story is that it's written in 1952, which is before chaos and the butterfly effect became widely appreciated in physics. In fact, the use of a butterfly here was completely coincidental. The term butterfly effect was created for other reasons somewhat later. So, okay, so it's a great story for that reason. It gets a lot right. But actually, the chaos is much stronger than the author of the story realized. So, in actual fact, if the time travelers had gone back in time and so much as disturbed the location of one atom by a millimeter, it would have completely changed the present in a way that would be unrecognizable. I mean, it's actually hard to imagine what would have happened, but it's like you would have re-rolled all the dice on 60 million years of evolution and whatever, climatology and meteorology. So I don't have any very good impression for what the world would look like, but the change would have been much, much more dramatic than just the spelling of a few words or a presidential election. So, okay, it's fun to think about that kind of thing, but that's not our goal. What I'm going to do now is we're going to transition slowly to talking about physics. We're going to discuss a thought experiment that you could use to test for chaos in a physical system. The first one we're going to consider is a bath of water. That's a highly chaotic, complicated system where small changes can lead to small effects later. But it's much simpler than thinking about the whole Earth. So it's a good thing to think about. So, okay, so this is part one. The first system we consider will be a bath of water. I'm not sure if this is legible. Like, can you guys see this? Okay, that's good. Okay, so I'm not a great artist, so here's, sorry, was that a, okay. Here's the bath of water. Here it is at time t equals 0. So this is the bath of water now. This is the water, and that's the surface. Now, to test for chaos in the system, we're going to imagine that the bath of water is in a very special kind of state. We don't know it yet, but it's been set up in a very clever way so that if we wait until a little time later, let's say t equals 1, maybe a minute later, that the bath of water will look substantially the same, except that somewhere on the surface a little whirlpool will have formed. So let's imagine, I mean, states like this are difficult to create in practice, but they exist mathematically. So we could imagine that some very clever person had engineered the state of this bath in just such a way that if we evolve forward for a little while, a small whirlpool will form at a definite location. So that's our starting point. Now, to test for chaos, what we do is we, at this time, we take this cleverly set up state of the bath of water, and we just take one of the water molecules and give it a tiny kick. And then we take that very, very slightly perturbed state and then wait a minute until this later time, and then we ask whether this whirlpool actually forms. And the claim is that in a highly chaotic system like this bath of water, the special event that would have formed in the future will not form. The whirlpool will fail to materialize from the bath of water. So in that way, we can determine that this system is chaotic. This is a thought experiment that we're going to repeat, so it's worth just emphasizing the sort of two steps. The first step, we set up a state which is carefully engineered so that something special is going to happen in the future. And then in the second step, we make a tiny, tiny change to that state, and then we ask if the special thing still happens. If it still happens, then the system wasn't chaotic, or at least not very chaotic. And if it doesn't happen, then it was chaotic. This is a quantitative way, somewhat quantitative way of thinking about the butterfly effect. So, okay, we know that this is true for the bath of water, but, well, at least at the level of drawing cartoons. But a bath of water is actually a very complicated system, and I don't know exactly how long we would have to wait, and I think to determine that would be a difficult problem. It would probably involve some input from experiments on baths of water, or maybe some computer simulations. It's just too difficult to keep track of all the particles interacting in the bath of water. So our second system sounds like it should be harder. That's a black hole. But actually, in this case, it will be possible to calculate this effect by hand. You might be suspicious that that means that the black hole is maybe only barely chaotic, or it's sort of stupid. But it turns out also that black holes are the most chaotic systems which are possible in nature. So it's remarkable that for those extremely chaotic systems, it's possible to do these computations by hand. Okay, so let's begin talking about the black hole. So for this, I'm going to draw diagrams which are space-time diagrams. And we should warm up drawing a space-time diagram without any black holes present. So the way the diagrams will work is that time goes up, and space goes sideways. And then we just have the space-time is the surface of the whiteboard. So for example, the trajectory of a particle moving first to the right, and then to the left, and then kind of staying still would be a curve through space-time that looks like that. So this is how we're going to represent the trajectories of particles which are moving through space-time, or moving through space as a function of time. Does this type of thing make sense? Because, well, anyhow, I hope you'll ask questions about that or anything else if it doesn't make sense.
Can you give us a definition
Of chaos? Yeah, so what? So the most essential thing is, well, it's that small perturbations to essentially any part of the system at one time can affect all properties at a later time. So there are many systems that are not chaotic. Like, for example, if we just have a bunch of particles, none of them are talking to each other at all. Then if I change the state of this one, it can't affect any of the others at all, just because they don't see each other. But for almost any system in nature, almost any physical system, it will be highly chaotic, because even if there are small interactions between the particles, that will build up over time, and changing the state of just one of them will eventually change the state of all of them. It's sort of funny that this is a totally generic property of physical systems, chaos. And it wasn't widely appreciated in physics for a long time. I think part of the reason for that is that chaotic systems tend to be difficult to study. Like if we're trying to study a bunch of particles, it's much easier to study that with paper and pencil if they're not interacting with each other at all. So physicists tended to focus on the systems which were easier to study by hand, and those are systems which tend not to be chaotic. So it was for that, I think partially for that reason, that it took people a long time to appreciate how important, how common chaos is. But then in the 50s and the 60s, computer simulation of physical systems made it possible to study this sort of regardless of whether you can do it by paper and pencil. Okay, so we got as far as describing this space-time diagram and showing how we would represent the trajectory of a particle. So now we want to introduce a black hole. So now we imagine that this space-time diagram is over here as well. So a black hole has two important places. One of them I'll represent with this dashed line, and the other one with this sort of squiggly line. This line here is called the horizon. And the rules are that once you pass the horizon and enter the shaded region, which is the black hole, you can't get back out again. So for example, an allowed trajectory for a particle would be something that starts out outside the black hole out here. It's going along, and then it falls into the black hole. Once it crosses this dashed line, it can't get back outside again. It's forced to continue in, and eventually it hits the singularity. The singularity is where space-time ends, and the particle has an unpleasant time at that point. So this is one type of allowed trajectory on the diagram with the black hole. Another type of allowed trajectory would be one where a particle is just barely failing to escape from the black hole. So it's traveling at the speed of light, trying to escape the black hole as well as it can, but it just barely can't. That would be a particle that's traveling just right along the horizon here. So that's another allowed trajectory. One that is just slightly inside the horizon might stay there for a long time, but eventually it will fall in. Another more interesting allowed trajectory is one that's moving at the speed of light, but starts just barely outside the horizon. That's one down here, so it's traveling along the horizon for a long time, but because it's slightly outside, it manages to escape. So this is a happy particle. Okay, so those are some trajectories that we can have in the black hole space-time. Now, for our discussion, there's an effect that's going to be important that happens when a particle falls into a black hole. What happens to the black hole when a particle falls into the black hole? Does anybody want to venture a guess? Well, the black hole gets slightly bigger. It gets slightly bigger because it's eaten the particle that fell in. So we can draw that like this. We redraw this horizon here. We have a particle that starts out outside. It falls in. And what it means for the black hole to get slightly bigger is that the horizon moves outwards slightly. The point of no return moves outwards slightly. So the horizon is here before the particle falls in. After the particle falls in, the horizon moves out a little bit, and something like that. If we're just throwing a light particle into a huge black hole, this effect will be very small. But this small effect is going to be important for our discussion. Okay, so that was all about particles propagating. Yeah.
Could you explain what the relationship is of a black hole with stars? Was a black hole originally a star?
Yeah, it could have been.
How many
Yeah.
black holes are there out there?
Well, there's lots of black holes. I guess the real number isn't known too well, but I guess a reasonable estimate would be some fraction of the number of stars. So there's supposed to be about 10 to the 22 stars in the universe.
Black holes?
Yeah, somewhat large stars at the end of their life will form black holes. There are other ways of forming black holes as well.
Supernovas or HEV stars?
Yeah, depending on the size of the star, it will either form a black hole or it will not. Okay, so now we'd like to set up this thought experiment that we did for the bath of water, but we'll do it for the black hole. So there were 2 steps in that, remember. First, we had to set up the state of the bath of the water in such a way that something special was going to happen in the future, and then we make a small perturbation to that state. So a black hole where something special is going to happen in the future, let's say that our time t equals 1 is up here. That could be a black hole where there's a particle. I'm going to try to use colored pens now, but I'm probably going to get confused. Where there's a particle which is traveling very close to the horizon, but it's on one of these trajectories where it just barely manages to escape. It barely manages to escape at t equals 1. That special event is a little bit like a whirlpool forming in the bath of water. So this is a carefully engineered state of a black hole where there's a particle here that's finely tuned that's just barely going to escape, and it emerges at t equals 1, a little bit like the whirlpool forming. So now the second step is we'd like to introduce a small perturbation to this system at time t equals 0. In the example with the bath of water, we just moved one of the water molecules within the bath. In this case, what we can imagine doing is throwing in one particle. So one tiny particle we throw into this enormous black hole. So we throw in the particle on some trajectory like this. And now we can ask what happens to our whirlpool. So when the particle falls in, remember what happens, the horizon moves outwards slightly. The horizon moves outwards slightly here. But now notice that the red particle, which was going to emerge, is behind the horizon. The black hole has gotten slightly bigger, and now it's big enough that the red particle can no longer escape. So the new trajectory of the red particle moving in the background of this slightly more massive black hole will look like this. And the horizon will be here. So the whirlpool does not form. Even though we added just a tiny, tiny particle to this huge black hole, it moved the horizon of the black hole out a very small amount. That was enough to capture this particle that was going to emerge. Yeah? Yeah, that's like, I mean, you should, it's because the black hole has some size before we throw in a particle, then we throw in a particle and it gets bigger. It's like, yeah. Yeah, sorry. The time goes up. So this is, the particle is moving. So here it is at t equals 0. Here it is a little bit later, a little bit later, a little bit later, and here it falls into the black hole. And at the time when it falls into the black hole gets slightly bigger. And from that point onwards, it's slightly bigger than it was before. Okay, so I told you that the nice thing about black holes is that you can do calculations by hand, unlike with the bath of water, but actually all I'm doing here is drawing cartoons. And I think you don't want me to go through all of the equations and show you how to analyze this in detail. But I can show you sort of one aspect of this, of the answer that you get, which is interesting. So it's helpful to think about, let's say, plotting something here. So what we're going to do is we're going to plot roughly the probability that the particle, the red particle gets out. And this is like the probability that the whirlpool forms as a function of how early we throw in the green perturbation particle. So, so this would be earlier. And this is later. So this is delta t. In the diagram here, delta t is this amount of time. So we could imagine throwing this green particle in earlier and earlier and earlier, or later and later and later. If we throw the particle in very late, it will expand the black hole slightly, but the red particle will already be out, so it won't have much effect. What that means is the plot of this looks like the following. The probability the particle gets out starts out as 1. It definitely makes it out. But as we push the time of the perturbation earlier, it can have a larger and larger influence, and the curve looks like this. So we can think about this as, for the bath of water, you would find a qualitatively similar curve. We would be asking, how likely is it that the whirlpool will form if we make our perturbation earlier and earlier and earlier? If we make it just like an instant before the whirlpool was supposed to form, it can't possibly interfere with it. But if we make the perturbation sufficiently early, then chaos will allow the perturbation to have a significant effect and prevent the whirlpool from forming. Okay, so that's the type of curve that one finds, and the form that you get in this region of the curve is the probability is given by 1 minus, I'll explain what this is in a second. I'll just write the formula. 1 minus this symbol, which is called g Newton. This is a small parameter which expresses the strength of gravitational interactions of matter. So this is a very small parameter in our universe. And then we have a factor which is growing exponentially in the time difference, delta t. Now, the rate of growth of this exponential is determined by the temperature of the black hole. That's this capital T here and this factor of 2 pi. So what you should think about this formula saying is that adding the particle makes a very small change to the black hole because g Newton, the gravitational interactions between particles, is very small. So it almost has no effect at all just because this parameter is so small. It's almost equal to 1. However, there's this exponentially growing factor which gets bigger and bigger and bigger the earlier you throw in the second particle. And eventually, this factor becomes large enough to drive the function to become small. Now, it's a very special property that we got this particular power here, e to the 2 pi times the temperature times this change in time. For a more generic system, you would have expected something qualitatively similar. Like for the bath of water, maybe we would have got something vaguely similar. But for a generic system, you would have expected something 1 minus something small, epsilon, let's call it, times e to the lambda t, where lambda is just some parameter that's sometimes referred to as a quantum Lyapunov constant. So the special thing about the black hole is it has a particular value for lambda, 2 pi times the temperature. And it was possible to prove that this is actually the largest value that is allowed in nature. So you could take any system that you like, and you could calculate something like this. You might get a form like that, but the parameter here, lambda, will be no bigger than 2 pi times the temperature. So what this means is that black holes are actually the most strongly chaotic systems that exist in nature. It's kind of funny because this sounded like such a trivial effect, this small increase in the size of the black hole, and this was something that we could discuss here, and something that you can compute precisely. But it's actually, although it's simple, it is describing chaos, which is the strongest chaos which exists in the laws of physics. Yeah. It will move if more particles fall in. Yeah, well, it only moves outwards when particles fall in. So the black hole gets bigger when it swallows something. But if you're not throwing anything into the black hole, it just sits there. The horizon stays at the same size. Yeah. Yeah, that's a good question. We can set this up in different ways, but it's possible. We could imagine that someone had set up a particle that was moving very close to the horizon at an earlier time. These states are somewhat unusual in the same way that it's unusual to find a bath of water in a state where a whirlpool is going to form in a little while. It's unusual to find a black hole in a state where there's a particle that's moving so fast, very close to its horizon. But those states exist in the same way that baths of water exist. Actually, okay, I don't know if this will be helpful, but one way to make states like that, how would you make a state where a bath of water, where a whirlpool is going to form a little while from now? You could start with a bath of water where you just add a whirlpool, and then evolve that thing backwards in time. That will give you a configuration that if you evolve it forwards in time, the whirlpool will form. So one way to create a situation like this with a black hole is to throw a particle into a black hole, and then consider that thing moving backwards in time. And the particle will emerge from somewhere very close to the horizon. Okay. So there's two other things I want to say. I'll make them both quick. So there's another type of system that people have found where it's possible to analyze this type of effect exactly. That was a system that was found by physicist Alexei Kitaev at Caltech. And it's a system where you have a lot of particles. There's no gravity, there's no black holes. You just have a lot of particles which are interacting with each other in sort of a random way, with random interactions. So you have a large number, n, of these particles that are interacting with each other. And he showed that it was possible in that system, if you assume all the interactions are random, it's possible to do a computation of the influence of one of the particles on another particle at a later time. And the type of formula that one finds in that case, I'm going to use P to represent the influence of one particle on a different particle at a later time, is like, it's 1 divided by the number of particles times something that's growing. In his system, 2 pi times the temperature times the time. So it's very similar to the formula that we got from black holes, except in place of the gravitational interaction constant G Newton, we have 1 over the number of particles. You can think about this factor in a sort of simple way. It's expressing the fact that one particle, if we have many particles, then changing the state of one of them won't have a very big effect, at least initially, on any of the other particles, because there are just so many. So the size of the effect will be 1 divided by the number of particles. But because this particle can interact with its friend, who can then interact with its friend, and his whole chaos thing can happen, the total influence can grow exponentially. 1 divided by n, the small initial effect, times this exponentially growing factor. And remarkably, the exponentially growing factor in this case is the same as for a black hole. This led many people to suspect that the system that Kitaev discovered might secretly be a description of a black hole. And that turns out to be the case. It's secretly a description of a black hole in a two-dimensional space-time, similar to the one that we were drawing on the whiteboard. This equivalence, it sounds completely crazy. Like, just a bunch of particles interacting with no gravity is somehow secretly equivalent to a black hole, which is a gravitational theory in a higher space-time dimension. But this is something which is sort of, by now, almost par for the course in some areas of physics. The first example of this was something that was discovered by Juan Maldacena, professor here 20 years ago, that in many cases, non-gravitational but strongly interacting quantum systems with many particles interacting with each other in a complicated way can secretly be describing gravitational theories in a higher dimension. And those gravitational theories can include black holes. So this is sort of a remarkable fact that he found this system, Kitaev found this system where you could compute this parameter and it matches a black hole, but it's part of a more general phenomenon of black holes being identified with strongly interacting normal systems. The final thing I'm going to mention is a puzzle that a lot of us are trying to understand. This puzzle has to do with this diagram for the black hole, which is in this case where we have an understanding of the black hole as a secret description of some highly interacting system of many particles. Then we know how to describe things out in the region outside the black hole. So if there are particles out here on some trajectory, we know how to describe these things in terms of the variables of the interacting particle system. So we have two systems that are secretly equivalent, and we know how to describe part of this system in terms of the interacting particles. But we don't know how to describe particles behind the horizon of the black hole, whatever they're doing. Actually, this wasn't a very legal trajectory. They're doing something like this. We don't know how to describe particles doing something like that. And actually, there's a group at Santa Barbara who proposed a few years ago that this region basically just does not exist. There aren't any particles propagating there. And instead of the horizon and then the singularity, you just have the singularity. So as soon as a particle falls in here, it immediately has a bad day. There's no region between the horizon and the singularity. This is a really striking thing that would be remarkable if it's true. But I think it's a very strange problem in physics, because this is a problem that, even in principle, cannot be resolved by doing an experiment, in a certain sense. So we could imagine building a black hole. Some advanced society has harnessed a black hole that they found somewhere, or they somehow got a bunch of matter together and collapsed it to form a black hole in a fairly quiet state. So there's no accretion disk, and so you can jump into the black hole. So in that case, we have this system here, and then we have a question. Is there a region behind the horizon, between the horizon and the singularity? There's no way for us outside the black hole to know the answer to that question by an experiment, because if you throw a probe in to check whether it's true, the probe will not be able to get back out. Once the probe crosses the horizon and it knows whether there was a region there, it can't tell you what it found. So there's really only one thing that you can do in this case by experiment. If you're really desperate, you really need to know the answer to this, you can jump into the black hole yourself. Then you'll know, but you can't write a paper about it. Or if you do, you can't tell your colleagues. So this is something that we can't answer by experiment. It's something, even in principle, it's something that we'll have to answer just by thinking about these systems harder. And that's what a lot of us are trying to do. So that's it. Thank you very much for your attention.